Hello everyone, welcome to tutorial number 7 in database CSEN 501. In the previous tutorial we talked about relational algebra and we have seen how to write the solution of a specific query in relational algebra. In this tutorial we are going to discuss the relational calculus, which is a language used to solve the queries as well. However, in relational calculus, we don't care about the procedure, we just care about the tuples we want. So, in other words, when we write the solution in relational calculus, all we care about is what tuples or what rows or what data we want to extract rather than how we are going to extract them. Okay, this is called the tuple relational calculus. Okay, how we write relational calculus? Simply, we just write here before this bar the tuple variable, and afterward we write the conditional expression involving. Let's take an example to understand what is meant by the tuple variable and what is a conditional expression. Let's assume that we have a relation called employees, and in this relation one of the attributes is the salary, and we want to get the employees whose salary is more than 50,000. Okay, let's divide this into two parts. First, the part we want to see as output. Okay, we want to see all employees, so we want to see the whole tuple or the whole row. Okay, we are going to represent the variable of employee by t. Okay, now we need to write what is meant by this t, or what does this t represent. Okay, we explain this or we'll write this after this bar. So we are going to write employee t, which means that t is a variable of employee. Okay, this is the first part. We want the employees under a specific condition. What is the condition? The salary is more than 5,000. Salary is an attribute in employee. The t here represents a variable of employee. Okay, and we want to get the employees whose salary greater than a specific amount. So in this case we are going to write and t dot salary greater than 50,000. Okay, so in this case we are going to extract the whole row or the whole tuple of employees whose salaries are greater than 50,000. What if we are not interested in the whole tuple or the whole row? We just want the names of the employees whose salary greater than a specific amount. In this case, we are going to specify this in the output. In other words, here we write t because we want the whole row. This will get the whole tuple or the whole row. What if we want a specific attribute to be the output? We want only the name of the employee. So in this case we are going to state this by writing t.name, and the whole expression or the conditional expression will be the same. The only difference that we want the name instead of the whole tuple. In relational calculus, we have two quantifiers for the variables. There exists and for all. How to use these quantifiers and when to use them? Let's assume that, for example, we have a relation student with name, course, and enrolled with course name and course ID, for example. Okay? And course references enrolled by course ID. So this one, the course ID is a foreign key representing the course ID. And we want to get the course names, the course name of a specific student. And we want to get, for example, the course name that student Ahmed is re-enrolled in. Okay? So the output here is the course name. So we are going to write this here. T or any other letter dot course name. This is the output, right? And we need to specify what does this T represent. This T is a variable of relation enrolled. Okay, so we are going to write enrolled T. Are we done yet? No, because we want the course name that Ahmed took. Okay, so we need to use this table, this relation. After this bar, no free variable should be written here. So we cannot write, for example, and as student. We cannot write this expression. In order to introduce another variable after this part, we should use one of these quantifiers, either there exists or for all. Okay? When to use for all and when to use there exists. If the output could be at least one or more, we are going to use there exists. If we expect that the output is true for all the tuples, then we are going to use for all. The example will explain it better. Let's continue here. Now we want the course name of student Ahmed, which in this case could be one or more. So we are going to use there exists. So we are going to write and there exists S, which is student S. In relational calculus, we should write the condition of the join by ourselves. So in this case, we are going to write and S dot course ID equals to course and S dot name equal Ahmed. The output could be one or more. Okay? Whenever we use for all, we will find that implies is used as well. So if we have an expression that uses for all, we will always find implies, or we actually need to use implies. We will see this later in the examples. Let's start solving the first one. Find the titles of all books whose author's first name is Herbert. Let's divide this into two parts. Find titles of all books. Which relation has the attribute title? Actually, this one and this one. This one and this one. Okay? So we can extract title from this or this. Let's move to the rest to know which one we are going to use. Whose author's first name is Herbert. Do we have here first name? No. Do we have here first name? Yes. So in this case, we can use only this relation in order to solve this example. What do we want to see in the output is the titles of the book. So we are going to write B dot titles, for example, where B. Okay? Whose author's first name is Herbert. First name is here, so we can write and B dot first name equal Herbert. Okay? Let's move to the second example. Find the first and the last name of all authors who have written books that have been published after year 2000. We want to get the name, the first name, and the last name of all authors. From where can we get this piece of information? From this relation or this relation. Let's move forward. Who have written books that have been published after year 2020. From where can we get the publication year? Actually, from this one. Pub date. Okay? What attribute is common between this one and this relation or this relation? Actually, title is common between these two both. So we can easily get the name of the authors who have written book in specific date using these two relations. So at the end, the output will be extracted from book. So we are going to write here B dot first name, B dot last name, book B. Now we need to introduce a new variable, which is edition. Okay? And in this case, it could be one or more. We want the author who have written one book or more. Okay? So we are going to use the quantifier there exists. There exists edition E, and we need to join between these two relations. The common attribute is title, so we need to say that B dot title equals to E dot title. Who have written books that have been published after certain years. So the publication date, which is E dot pub date, greater than 2000. Okay, let's move to another example. Find the pairs of edition represented by the ISBN that are of the same book. A pair should be listed only once. IJ, sorry, not JI. This is the same one as we solved in the previous tutorial using relational algebra. We want to see in the output a pair of edition, which means that we want to see the ISBN twice. Okay? In the previous tutorial, we did so by self-joining edition by itself. We join edition by edition. So at the end, the output is two columns. Each one is extracted from relation edition. So the output is ISBN, ISBN. So we are going to write here E1.ISBN, E2.ISBN, where edition E1 and edition E2. Okay? What is the common thing, or how actually we are going to join these two editions? We want editions of the same book. Same book means same title. So we need to state this E1 dot title equal E2 dot title. And we want the ISBN to be listed once, which means that if we have a pair of R1, 2, we don't want to see 2, 1. We did so simply in the previous tutorial by putting an extra condition, which is e1.isbn, for example, less than e2.isbn. Find the publisher who have published books by Grace Pell. Okay, we want the publisher. From where can we get publisher? From edition. Okay? Are we done yet? No, because we want the publisher of a book with a specific author. From where can we get the book with its author? From relation book. So at the end we are going to use these two relations in order to solve this query. Okay, what is the output, or what do we want to see in the output? We want to see publisher from table edition. So we are going to write e.publisher edition E. Are we done yet? No, because we need to join between these two tables. So we are going to introduce a new variable book. And there exists book B, and we need to join, and e.title equal b.title. Okay, and b.first name equal race, and b.last name equal. Okay, find the name of bookstores selling all edition. Okay, in the previous tutorial we solved this in relational algebra by using the division operator. Let's assume that we have here table bookstore, stock with the store name, the ISBN, and edition with ISBN. Okay, 1, 2, 3, 4. X1, Y2, X3, X2, Y1, X4. If we want to know the output in this case, what is the store name that sell all the edition? Okay, actually if we check X, we will find that X sells edition 1, X sells 3, 2, and 4, which means that X sells all the edition. Y sells 2 and 1, so the output will be X only. Okay, first let's write from where can we get this piece of information, or from which relation we can get the output of this query. We want the name of the bookstore selling all edition. The relation that have the bookstore and the corresponding edition is stock. So we can get the store name from stock. Can write s.store name. Stock S. Okay? And we are going to check that this store name sells all the edition from table edition. Okay, actually we want to make sure that this store name sells all edition. Since I say all, this means that edition will be introduced by for all quantifier not there exist. because I want the store name that sells all the edition. That is true for all the tuples in edition. Okay, and that's why when we are going to introduce edition, we are going to use the for all quantifier, for all edition. Okay, we stated that whenever we use for all, we should use implies. So for all edition, this implies. Okay, what do we want? We want to check that this store name sells all edition. So if we are pointing here in X, we want to check that X is selling all edition. Okay, some will suggest that we can simply write E.ISBN equal to S.ISBN. Actually, this is wrong. Why? Because if we do so, let's assume that S is pointing here. So in this case, the ISBN is 1 and E.ISBN is 1. So this is correct. Then the next row, we are going to check the next row with the next row. The next row is 2. We are going to check this row against the next row here, because we say that for all for S, all E's should be true. So in this case, S is pointing here. ISBN is 1, and in this case, ISBN is 2. So this will return false. However, actually should return true, because if we check below, we will find that X has ISBN 2. Okay, so in this case, actually we want to make another variable that is of type stock and point to the next X. So if the first S is X, we want, in this case, after checking 1 with 1, the first row with the first row, we actually want to move the pointer to the next X, which is 2, and check it against here. Okay, so in this case we need to make another variable with the same store name to check all the X's against the ISBN here. So in this case, we are going to check if the X having the same ISBN. If it's true, we are going to move to the other X, and so on. So we are going simply to get the first row, check the store name. If it is X, we are going to make another variable of the stock with the same name and check all the rows of this specific name to check the ISBN of this rows against all the ISBN here. So in this case, we need to introduce a new variable of stock. So we are going to say, and there exists S1 stock and S1.store name equals to S.store name. Are we done yet? No, because we want to check the ISBN with the ISBN of edition. Actually, we want to check the ISBN of S1, not S, because we want to check the ISBN of all the X's while keeping moving down the table to check the ISBN of all X's. So we are going to write S1.ISBN equals to E.ISBN. Okay, so in this case, we are going to say that we want the store name, and for all editions, there exists stock with the same name that have all the ISBN that is found in edition. Okay? Let's take another example. We can conclude that most of the time we use for all in the cases of division of relational algebra, when we should check the tuple against all or with all the tuples of a specific relation. Okay, so in this case we use for all. Let's take another example. Consider the relational schema represent the JC eBay. We have sellers, items, buyers, stock, purchase. Okay? Find the ID of buyers who purchased items of a purchase quantity less than 10% of the quantity provided by the same seller in the stock. Let's divide this query into parts in order to understand what is the requirement of this query. First, find the IDs of buyers. We want to get the ID of buyers. If we check here, we will find that we can get it from buyers or from purchase. Let's move forward to know which relation we can use. Who purchased items of a purchase quantity? Who purchased items? From this part, we knew that we want the buyers who have done purchases. Okay, so this means that we are going to get them from this relation. So we are going to write P dot buyer ID purchase P. Okay, of purchased items of a purchase quantity less than 10%. We can use the purchase quantity in this relation. Less than 10% of the quantity provided. The quantity is found in stock, so we should use this relation as well. Provided by the same seller. So when we use or when we join this relation with purchase, we need to state that they have the same seller and the same item. So we are going to introduce another variable, which is stock, and there exists S stock S and S dot seller ID equals to P dot seller ID and S dot item ID equals to P dot item ID. Let's check the condition. The purchase quantity less than 10% of the quantity provided. So the purchase quantity should be less than 10%. When we say 10%, it means 0.1 times quantity. Okay? And purchase quantity is found in purchase. So we are going to write P dot purchase quantity less than 0.1 times the quantity is an attribute in stock. So we're going to say S dot quantity. Okay, let's move to another example. Find the ID of the buyers who purchased items. The ID of the buyers, we can get it from this table or this table. However, we want the buyers who purchased, which means that we are going to get it from this table. So we are going to write P dot buyer ID. Okay? Purchased items with type furniture. From where can we get the type of an item? We can get it from table items. So we are going to join between purchase and items. We are going to introduce a new variable, so we should use a quantifier. So we are going to use there exists item I, and we should write the condition of the join. Okay, what is the common attribute, or how can we join between purchase and item? Using item ID and p dot item ID equals to I dot item ID. Okay, of type furniture, the type is in items, so we can specify this by writing I dot type equal furniture. Are we done yet? No. For over 10% of the start bid of the price of the item they bought. So we need to compare the start bid, or actually to have a condition between the start bid, which is found in stock, and price, which is found in purchase that we already have. So in this case, we need to introduce stock as well in our solution. So we are going to introduce a new variable stock. Okay, how can we join between stock and purchase? Okay, we need to join between these two, which is in this case we need to check the common attributes between these two relations, which are item ID, seller ID. So we are going to introduce another variable, which is stock. There exists stock S, and we should write the condition of the join S dot item ID equals to P dot item ID and S dot seller ID equals to P dot seller ID. Are we done yet? No, because we need to check the condition that we want to write in this case. We want the ID of the buyers who purchased items with type furniture for over 10% of the start bid. So we want the price to be greater than the start bid by 10%. Okay, so in this case we want the price to be larger than the start bid with 10%, which means that the price should be 1.1 times the start bid. Okay, so since the price is attribute in purchase and start bid is attribute and stock, so we are going to write it as follows, where P dot price greater than 1.1 times S dot start bid. From where can from where we got this 1.1? Because if we have a start bid, for example 10, and we want to check those who have price over 10%, which means that the 10% of the 10 is 1. So we want to get the price greater than, or actually more than 10% of the start bid. Okay, so if the start bid is 10, we want the price which have the start bid plus 10% of the start bid, which is 1. Okay, that's why it is written as follows. Let's move to another example. Find the IDs of buyers. From where can we get this info? Either from purchase or from buyers, who either always make a purchase with a purchase quantity less than 5 or haven't made any purchase. So in this case, we want the buyer IDs who either make purchase with purchase quantity with a specific amount or haven't made any purchase. Okay, from where can we get both buyers who made purchases and haven't made any purchases? Actually, we can get it from table buyers, because table purchase have the buyer IDs who have done purchases only. So the relation that we can use in order to get the ID of buyers, of all buyers, is buyers. So we are going to write B dot buyer ID buyers B. Okay, now let's take an example to understand how we are going to solve this problem. Let's assume that we have table buyers, buyer ID 1, 2, 3, 4, and we have table purchase with buyer ID and purchase quantity. Buyer ID 1, 3, 2, 4, 1, 6, 2, 3, 3, 2. Okay, let's see which of these buyer IDs should be part of our output. Let's check buyer 1. Buyer 1, what is the purchase quantities that buyers 1 have done? Okay, 1 have done purchase with quantity 3 and another purchases with 6. Is this considered to be a purchase quantity less than 5? No. We want the IDs of the buyers who always make purchases with a purchase quantity less than 5, which means that if it happens that we found a row of this buyer with a purchase quantity greater than 5, it means that this buyer will not be included in our output. Okay, so 1 is not part of our output. Let's check 2. 2 made a purchase quantity with 4 and with 3. Both are less than 5, so 2 is part of our output. 3 made a purchase quantity 2, which is less than 5, so it is a part of our output. 4 haven't made any purchases, which is part of our output because we want the ID of the buyers who always make purchase with a purchase quantity less than 5 or haven't made any purchase. So at the end our output will be 2, 3, 4. What actually we did to check each buyer with its purchase quantity. We get the ID of the buyer and we check all its purchases quantity. Since I say all, this means that we are going to check the buyer ID across all its tuples or across all its purchases, okay, to make sure that its purchase quantity less than 5. This means that when we introduce purchase here, we are going to use a for all quantifier because we want to make sure that this buyer, all its purchases, not only once, all its purchases are less than 5. So we are going to write for all P purchase P. Okay? And we need to relate the buyer with the purchase. Actually, they are related using the buyer ID. We want to check actually the rows of this specific buyer in table purchase. So we are going to state b.buyer ID equals to p.buyer ID. After for all, we always should write implies. Implies. We want to check all the purchases of this buyer, making sure that all the purchase quantity is less than 5. So if it happened that we find a row where the buyer ID equals the PID, we want to check this buyer ID against all, or actually with all the rows, making sure that in this case P dot purchase quantity is less than 5. Okay, are we done? Yes or no? We need to check whether this will return the buyer that haven't made any purchases or not. Okay, let's take an example. Now buyer 1, okay, buyer ID equals to buyer ID. All the purchase quantity of this buyer ID less than 5? No, because in this case it is 6, so 1 is excluded. 2, buyer ID equals to buyer ID. So we are going to check the purchases quantity for all this buyer ID. 4 and 3 actually less than 5, so it's part of the output. Okay? Now, buyer 3. Buyer ID equal buyer ID, which is this row. The purchase quantity is less than 5, so it is part of the output. Now, buyer ID 4. Do we have here in table purchase a row with buyer ID 4? Actually, no. So, in this case, this condition will be false when we are pointing to buyer ID 4. Okay, because there is no row here with buyer ID 4. So, in this case, this will be false. Actually, false implies anything will always return true. So, in this case, this whole expression will return true. So, the 4 will be actually returned because false implies anything will return true. So, the 4 will be part of our output, which what we want, because we want the buyers who do not have any records here in purchases, which is the case here. Okay? And that's why this expression will actually get us the buyers who make purchases with quantity less than 5 or who haven't made any purchases at all. This is for today, and next time we are going to have a tutorial on some queries on SQL. See you next time. Take care and see you soon. Thank you very much.